Yeah, so am I audible? Can someone confirm?
Yes, sir.
Yeah, okay, fine. I will be starting now. Let me share my screen first. Yeah, so is my screen visible?
Yes, sir.
Cool. So let's start. So today's session I will not be covering any. I will not be summarizing anything. I will just be solving some problems. I hope everything that was covered in the in the week's lecture you were able to understand that, everyone, right? So noise, I don't think anyone has any problem, at least in the basics of it, whatever was covered. Cool. So I will be starting in that case with the problems. Before that, quick introductions. So this is again analog IC design. This course is analog IC design. It's an NPTEL course, and it is the instructor for this course is Dr. Sankaran Aniruddhan. He's from IIT Madras. He is from the Department of Electrical Engineering. And myself, I hold these sessions or problem solving sessions. My name is Mayank Anupam. Anupam. I am a PMRF scholar. I am from electrical engineering from IIT Kanpur. Okay. So proceeding with this week's first problem. So yeah. So this question is actually basically we have to find. Do you understand what is signal to noise ratio?
Yes, sir.
Yeah. What is that signal to noise ratio?
Sir, output signal voltage by noise
No,
voltage.
not correct. It's not that. Yeah, you are thinking correct lines, but yeah, there is some
It's
problem with
mainly sir
notation.
power.
Yeah, correct.
Power.
It's actually power, power output signal power divided by output noise power. Okay, that is what is SNR. Cool. Fine. So we write it here. Uh, so SNR. Let's say signal to noise ratio. Sort is SNR. It's actually defined as output signal power divided by output noise power. Okay. And uh, okay, so this is signal power and output noise power. Okay. Now you remember that noise is a quantity which we quantify in terms of its spectral density, right? Its power spectral density. We do not say noise in terms of absolute voltage or current, right? We quantify it in terms of its spectral density, right? So when we talk about what is spectral density, by the way, what is noise spectral density? Anyone? Sorry, noise power spectral density basically. Yeah, anyone? What is noise power spectral density? Short is PSD, denoted as SVN or SIN, whatever you want to call it. SVN if it is voltage, SIN if it is current. So what is it?
So energy content per frequency, like
Correct.
per hertz.
I mean power content per unit frequency, something like that. Okay, it's the power of the energy, power of the noise at some particular frequency. Power density, basically it is the density. So if you have a noise spectral density like this, okay, if you plot in this manner, this, let's say it is SV, we are concentrating on voltage spectral density, okay, and this is versus frequency. Then if you take a unit 1 hertz bandwidth here, okay, at some frequency, at some f0 you take a 1 hertz bandwidth, then the power content in this, that is the PSD at this frequency f0, okay. Is that clear? Cool. So this is basically PSD at f0. Okay, now so these things are now that we are on the same page, now let's quickly solve this question. So this question is very similar to the one that is there in the assignment also. It has basically a MOSFET here and another MOSFET here. These two are in cascode, okay, and the output is taken here. There is a current source here, okay. Now you have to find out, you have to assume for this case, first of all, that all the this thing you can assume here is that 1 second, yeah, for this question you can assume that all the MOSFETs, you can assume that their output resistance are infinite, okay, for all the MOSFETs. Basically you can neglect channel length modulation here, neglect CLM, okay. So this G2 and this is G1, we can assume G1 is equal to G2 and they both are tending to infinity, okay, sorry, not infinity but 0, actually 0, not tending to but equal to 0, assume. Fine. So basically for the first part, assume CP is equal to 0, so we assume this is also not there, okay, and these two are not there, G1 and G2 are not there here, so then nothing remains, yeah. So in that case, find out the signal to noise ratio here at V0. What is the input referred noise? So how do we proceed with this question? First one, anyone, any idea? Yeah, any idea? Okay, so the question is that basically, yeah, small signal analysis correct, but how? I mean, so first let me rewrite the question here. We have a current source here at the top, which is VDD. Then we have this MOSFETs. We have some small signal plus some large bias here. This is another bias here. Cool. And we have assumed that there is no capacitor here, right? On the second part, this is M1, this is M2. Okay. Now this is the output. So one way to do this, we have to find out, right? We have to find out the small signal noise to signal to noise ratio, right? So for signal to noise ratio, what is the signal to noise ratio? It is output signal power divided by output noise power, right? So we have to find out the total noise power, right? Signal power is easy, simple. Signal power is easy, right? You can simply find the small signal gain between the input here. This is the input and output. You can simply find the small signal gain and simply multiply your input signal to the small signal gain to get the output signal here. So in output signal power is easy, okay, but input signal power, sorry, the noise power we have to calculate. So how do we do that? First of all, can you identify which of the devices, which are the entities which will contribute to the noise, overall noise of the circuit? Yeah guys, someone please speak up. Cool, transistors. So right, so only the transistors current source, you can assume that it is ideal and it does not contribute to any output noise. Okay, you can assume that the noise, this current source is ideal, no noise. So the only two noise giving term entities are basically this MOSFET here. Okay, sorry, use another color here. And another is this MOSFET right here. Both of these, they will contribute to some noise. They have some noise, right? They have some noise. And what is this noise, by the way? This noise here? Yeah, thermal noise. So what is the equation for that thermal noise? What is the expression for the thermal noise? It's 4 kT some factor gamma or eta, whatever you want to say, times gm2, right? Similarly for this it is 4 kT some gamma gm1. Okay, so these are the noise terms here. This is a noise spectral density, by the way. Noise current spectral density. This is also noise current spectral density. Okay, now tell me, yeah, so now we have to find out what is the total noise voltage we at this output terminal. What is the total noise voltage? That is what we have to calculate. Fine.
Sir, will it be 8 by 3 KT? Like,
Yeah, actually gamma can approximately be 2 by 3 for long channel
okay.
devices, but for short channel gamma is actually very close to 1. Okay, so you cannot say anything, just assume that it is gamma, some gamma. We do not know what it is, we do not need to know also. Okay, if someone wants to calculate, someone wants you to calculate everything, then they will explicitly mention what is the value of gamma. Okay, but yeah, for long channel devices, you can assume gamma is actually equal to approximately equal to 2 by 3. It is in saturation. 2 by 3 is in saturation. Fine. So let's yeah. By the way, you also have to assume that there is a resistance connected at the output. There is some resistor RL, load resistor connected at the output. Okay, or else the noise voltage will become infinite. There is some load resistance here. Okay. Yeah. So let's write it. This is RL. This is VO. Yeah, so now tell me what will be the output noise voltage because of these two current. By the way, these currents, they are small signal. Okay, they are small signal currents that I have drawn here. So what is the how will you proceed? How will you proceed to find the voltage, output noise voltage?
Sir, we find the transfer function from
Correct.
each of the
Correct.
source.
Yeah. So why do you say that? Why do you say that each of these? Why do you say that?
Actually, two current source, they will contribute different noise.
Correct. True. So I just want to hear that term. So basically, you are in referring to this thing, right? Principle of superposition, isn't it?
Yes,
Since
sir.
basically there are two independent current sources. Okay, and in a linear circuit. So when you write its small signal equivalent, this will become a linear circuit, right? And after that, since there are two current sources, as a linear circuit, we can use principle of superposition, right? We can individually find their effect at the output and then sum them, right?
Yes, sir. Actually, they are uncorrelated.
Yeah, they are uncorrelated, right? And that will help us to find to further simplify it. But before that, even if they are not uncorrelated, if these two are simply some current sources which are not uncorrelated, even then you can apply principle of superposition, right?
Yes.
Because this is a linear circuit, you can apply principle of superposition. So individually we have to find out what is the effect of the both these current sources, right? Yeah, so let's first take M1. Okay, so let's write, we will find the, and for timing, let's not write it 4 kT gamma gm2 and gm1. Let's just write it in terms of is IN2 is IN1. Okay, so we'll find the total noise voltage at the output to the individual current sources and finally add them using the principle of superposition. Correct. So let's first take take iron one. Okay, so when I have to only consider iron one, what should I do with iron two?
Sir, it is open circuit.
Correct, is open circuit, right? So let's do that now. And what should I do with this I naught current source?
Sir, also open circuit.
Correct. So basically we have the following picture. We have this MOSFET here. This is simply open, right? No, sorry, this is not open. There is a resistance RL here. Okay, and this is V out. Then there is and this biases and this input signal. These are also what? What should we do with them?
Zero, grounded.
Grounded, right? So we have to ground this, and another this is also grounded. Then we have this current source. This is IN1. Yeah. So what will be the output voltage due to this IN1? Tell me, what will be the output voltage V out due to this IN1? This is GM2, this is GM1. Okay. So what will be the output voltage?
Sir, we can neglect channel length modulation.
Yeah, we have to neglect channel modulation. Yes.
Then it will be just RL into IN1.
Correct. So how did you find that? How did you come to that conclusion?
Sir, just a constant current source following through the whole circuit. So that.
Correct. So basically, you see, this is a very simple thing to understand actually. Those people who are not able to follow, let's see. Uh, this guy here, okay. This guy here, if we consider it a box, if we consider a box around it. Oh my god. If you consider a small box around it like this, correct, and you see that this MOSFET here, this MOS oh yeah, this MOSFET here, its gate and its source are both grounded, right? So its output current will be zero, isn't it? It will not be contributing any current. Am I right? Am I right? So people, please be a little attentive here. I mean,
Sir,
if you do not
actually, I have a doubt. Uh, like in biasing,
huh?
so that I can, like sir, if we explicitly apply 1 volt source for biasing,
Huh?
and then we again explicitly use a VGS is less than the VTH, then what will be the, like, in which region the MOSFET is working?
I didn't understand your question.
Actually, sir, I biased with 1 milliamps current,
Hmm?
the transistor,
Mm-hmm.
and we explicitly again use VGS is less than VTH. Like we can use VGS is like 0.5 volts,
Mm-hmm.
and our VTN is 1 volt.
Okay.
So then what will be the condition of the
That will
transistor?
be in sub threshold. Okay. So that is something which is not to be. I mean, this is beyond the scope of this particular course. I don't think sub
And
threshold is there.
then sir, again another question, like if our VDS is less than VGS minus VTN,
Mm.
and we are applying on milliamps currents, then which region the transistor will be working?
I am not understanding. I again didn't follow your question. So,
Actually sir,
first, you are saying that VGS is less than VTH, and then you are saying VDS is also less than VGS minus VTH.
no, second, first case is ignored.
Okay.
First case is valid, like VGS is greater than VTN,
Okay. Okay.
and then we apply explicitly 1 milliamps voltage source,
Mm-hmm.
and our VDS is less than VTN minus VGS minus VTN, then it will be in linear
Linear
region,
region.
right?
Yes.
Okay.
Cool.
Yes.
So anyway, back to this question. So I was saying that yeah. So basically, in this particular MOSFET M1, this is M1, right? This is M1. In this MOSFET, you see that gate is also grounded, the source is also grounded. So the current flowing through this MOSFET has to be zero, right? Current through a MOSFET is what? GM times VGS. You see VGS here is zero, right? So that is why this MOSFET is out of the picture. Okay. So let's remove it from the picture in that case. Okay. Now you see that this ion one is only has one path to flow, right? It can only go into this MOSFET here, correct? Now if it goes through this MOSFET, the only thing that from this terminal, if you see, it has to come out of this terminal, right? It cannot flow anywhere else. If this current is flowing through this terminal, it has to come out through this terminal, correct? And this current will flow through this RL, exactly. So that is why the overall current in this case, let's again put it here, this is M1, this is M2. So basically in this case, the SV out due to M1 is what? It's actually equal to not SV out. Let's first what is the noise voltage? Vn due to M1. As one of your friends said, it is actually equal to IN1 times RL, right? Cool. Now this is the first one. Let's write it. Now let's take the second case. Now take IN2. Okay. And basically this is the same picture, isn't it? We just have to take the IN2 in this case. This is again grounded. We have again this condition here, this RL here. This is V out. There is a noise source here connected to drain and source. We have the second MOSFET. It's grounded here. It's also grounded. And the second MOSFET's noise current is desensitized, right? It is open. Now tell me, what will be the output voltage? What will the output voltage in this case? Incremental output voltage, what will it be?
Shouldn't it be zero?
Yeah, why do you say that?
So the lower MOSFET is off.
Correct. So lower MOSFET is off, exactly. So you see this is out of picture. You see that in this case also, this is 0, right? VGS is 0. So that this is out of picture. So you can see this terminal is hanging here, right? It's simply not connected to anything. It's simply hanging. This terminal is hanging. So if it is not connected to anything, if it is hanging, this current here, whatever current is flowing, IN2, it cannot flow here, right? Because if it flows here, if something comes out of this box, here, it has to again come back, right, from somewhere. But that somewhere is not that coming back is not possible here, because this node is hanging, right? So that is why in this case the current IN2 is not going to flow out. So voltage V out due to IN2 is actually equal to 0. So Vn of due to M2 is actually equal to 0. Okay. Fine.
Sir,
Fine.
one question, sir.
Yeah, go on.
Sir, as the source of this MOSFET is like open,
Hmm.
so there will be some noise, like, right? So we are considering the all noise in I into,
I
like if
didn't get your question. What are you saying?
sir, for open terminal, what voltage in that open terminal we can say, like small noise voltage, right?
Yeah, there will be some voltage here. Yes, at this node. Correct.
And sir, this noise is included in the IN2. We can say that. Can we say
This,
that?
no. Actually, what is happening is the voltage that is being induced here, this voltage here, okay, it's only happening because of IN2 only. First of all, there is a current here IN2 which is flowing here inside which is going to flow here. Okay, it will simply loop in this particular loop here. Okay, it will simply loop here in the MOSFET only, and because of that only this source voltage is moving here. Okay.
Okay.
Okay, cool. So fine, we have calculated both the voltages, right? Vn of m1 and Vn of m2. Now what is the what is the total noise voltage at the output? Total noise voltage at the output. What will it be? Yeah, what will it be?
IN1 times RL.
Yeah, correct. So basically it is Vn of m1 plus Vn of m2, correct? And since Vn of m2 is 0, so it is In1 times RL plus 0, correct? And this is the total noise voltage, which is basically equal to In1 times RL, correct? Now what is the power spectral density in that case? So what is output noise voltage PSD, so also SV out, what is it? Yes, what is it?
SIN times RL square.
So it is actually equal to, so what is the formula, by the way? It is actually equal to In1 RL the whole square and average of it, right? That is what it is, mean squared. It is basically mean squared, and when you open it, it will be In1 square average times RL square, and this In square average is basically called SIN, what one of you said, and times RL, In1 times RL square. So what will it be? 4 KT gamma times GM1 times RL square, right? Is that clear?
Yes, sir.
Correct. Now tell me something. If this was not 0 here, if there would have been some other than 0, it would have been a non-zero number. So let's say let's say that Vn of 2 is not equal to 0, okay, and Vn of 2 is actually equal to something like some m, okay, m times some m times In2, let's say, okay. So in that case what will be the total noise voltage at the output? Yeah, someone.
We have to add the second one also.
Yeah, so
And if they're not correlated, then it would be simply.
one second, hold on. So we have to add the second one. So let's say it is m times In2, okay. Yeah, now it is this is the total noise voltage at the output. So what is the PSD?
So it will be the square of that, mean square of that. But
Correct,
if they're
mean
not
square.
correlated, then.
Yeah, good. So that is what I wanted to clarify. We have to square and take the mean, right? Square and then take the mean. It is not mean and then square. It is square and then mean, right? And what will it be? So let's do this exercise once. So it will be what? In1 square times RL plus m square times in2 square plus 2 times m times RL times in1 times in2. Correct? This is what it is, and then the whole average. Correct? Yeah. So now tell me, you have heard it, you must have seen it in some statistics class. If the what is the mean of a sum of different variables? I mean here this is actually equal to what? This is actually equal to mean of individual items, right? Actually equal to
Yeah.
mean of this plus mean of this plus 2m times RL times in1 times in2 for the whole mean, right? This is what it is. Okay. Now is what should I do now? So as one of you pointed out, if in1 and in2 are uncorrelated, okay, so what happens is that if two random variables are uncorrelated, if two, this is basically this in1 and in2, they are statistical parameters, right? They are statistical quantities, and if they are uncorrelated, in that case the mean of their multiplication is simply the multiplication of their mean. Do you get what I'm saying? So this is basically equal to, or let's ignore this, let's only consider this one. So in this case, this can be written as 2m times RL times mean of their individual multiplication. Sorry, the multiplication of their individual means. Okay, and as you already know, the mean of we have assumed that these noise quantities, they are zero mean. Okay, so we have assumed assumption is that mean of I1 and in2 are both zero mean. That is why this quantity is 0, this quantity is 0, so they multiply, so this whole quantity becomes 0. Okay, so this is just what I wanted to clarify. Cool. So here that was not a problem, right? Here this was not a problem in this case. It was easy, simple. So it was a simple digression. Let's write it. Let's put a box around it. Okay, now moving on. Yeah, so can you tell me now what was it that made that basically ensured that the noise contribution of M2 was 0? What was special about this circuit which made sure that the so what I'm asking is, what is special about this circuit which ensured that the noise contribution of M2 was 0 at the output? Why did that happen?
Source is not bad.
G1 and G2.
Yeah, go on. Yes.
G1 and G2 is 0.
G1 and G2 is 0, correct. So what okay, so let's say if G2 was not 0, even if there was G2, okay, so let's say G2 is there. So
Sir,
one second. So if G2 is there, okay, so now will there be some output contribution due to M2? So look at
No,
this.
sir.
Look at this figure. So do you think that if there was some G2 here, something would have been different here?
No,
sir.
sir.
Right. So it is basically not G2 but G1. When we ensure that this G1 is 0, that made sure that the contribution of this noise current of M2 was 0, right? Correct.
Yes.
And now I want you to develop your intuition basically. So, and what is when G2 when G1 is 0, what is happening actually? Any current which is going to be generated in M2 cannot reach out, right? Because this guy here is simply turning off. So any current that will generate inside it will simply loop inside it only. M2 will loop inside M2 only, isn't it? So that is why it is essential to have some something which can ensure that the current can leak out here, right? Only then can M2 contribute to the output noise, right?
Yes.
Fine. Now let's solve the second question because of that. So on that basis, yeah, so basically this is the second question which I already discussed. What is the contribution of the noise of M2 at the output and why? So basically M2 has no contribution, right? And because there is no path for current of M2 to flow. Cool. Now assume a finite CP. Oh, by the way, this question is not solved here. Okay, we have only found out what is the total output noise PhD. Okay, but we had to find out SNR. So for SNR, what do? We have to find the output noise power. Okay, we have to find out total output noise power. So for that, what we have to do, we have to know what is the signal bandwidth. Okay, this is the noise power spectral density. 1 second. Yeah, so let's do this first. So we have SV out is equal to what? 4 kt gamma gm 1 times RL square, right? And what is this? It's power spectral density, right? It's the power spectral density. It is not the power but the density of power. To find out the total power, what do we have to do?
We integrate it for
Correct.
some bandwidth.
SV out times df. We have to integrate from 0 to infinity, right? Isn't it?
Yes.
Correct. Now, so that is why so when you integrate it SV out df times 0 to infinity, so basically this is total power, assuming that your noise, your signal is also from 0 to infinity. So that is not generally the case. You can assume that the signal has a finite bandwidth. Okay, so let's say your signal is only from let's say your signal is only from here till here. Okay, so there is no point calculating your noise from here to here everywhere, because your signal is only from here to here. Okay, from let's say some bandwidth B. So there is no point in calculating noise from here everywhere, because noise outside of this, they will not be affecting your signal at all, isn't it? So basically it is the bandwidth of the circuit which matters. So we have to find out, let's assume that the bandwidth of the circuit is some B hertz. Okay, in that case total power is what? Noise power is equal to 4 kt gamma gm1 times RL square times df 0 to B, right?
Yes.
Correct. And this will be equal to what? Equal to 4 kt gamma gm1 times RL square times B. So this is the total noise power, right? Right?
Yes.
And what is signal power?
Excuse me.
Yeah.
Here, why we are not adding load resistance thermal noise?
Yeah, we did,
Null.
right? Oh, sorry. So I forgot to mention. So just assume that the load resistance output noise is can be neglected. Just assume that. It doesn't matter if you can add it. It doesn't matter. You can add its output noise. It will simply add a constant term here. It will add some term here. But
Yes,
the
sir.
point of this question was not to emphasize on RL. It was to emphasize this particular thing that we did. The procedure here that we took here. Okay.
But basically, RL is used for not infinite noise, right? If RL
Yeah,
is not,
there will be definitely some always some load connected at the output, right? There will be something. So here is just RL. I just assume that RL is noiseless, but yeah, so that is true. RL will also contribute to some noise, but let's assume that it is noiseless, because the point of this question was to show this, illustrate this particular uh, thing here, that M2 does not contribute to noise but M1 is contributing. This is a very important concept, by the way.
Here we are neglecting thermal noise of RL, right?
Yeah, we are neglected. Yes. Right. So let's move on. What is signal power here?
Sir, GM1 into the output resistance of the whole circuit.
GM1 times RL times anything else?
Parallel. Yes, parallel.
Okay.
1 plus GM2
I assume that
RO2.
I have already assumed, right, that the output resistance of these two MOSFETs, M2 and M1,
Yes, yes, yes,
are
yes.
what?
Infinite. Yep.
Infinite, right? So it is RL parallel infinity. So it will be simply GM1 times RL, correct?
Yes, sir.
And what is signal, input signal, right? VI,
Yes, sir.
correct? And this will be squared, isn't it? Because we are talking about power. Is that clear? Excuse me, is that clear? Is this clear? Okay. And this will be then multiplied with the bandwidth of the signal. Right? This is just a crude calculation. But anyway, this is the point here that I wanted to make. This is the signal power and this is the noise power. Okay, and we'll simply, SNR is simply what? Signal power divided by noise power.
So, sir, in signal power, why bandwidth is multiplied?
I mean, you have to take some bandwidth for a signal, right? I mean, here there was ideally you have to integrate your signal like this again for the signal also. For total power you have to integrate it. You have to do this DF thing again here, and when you do that you will get this particular item here. Okay.
Okay, sir.
Sir, I have a doubt.
Yeah, go on.
In the signal power, shouldn't it be GM1 times VI square into RL? Because GM1 times VI is the current flowing through RL. And if
Yeah,
there is I flowing through RL, then its power should be I1 square into RL, right?
into RL square, right?
RL square? I
Okay,
square
okay,
R is power.
1 second. So that is why I went step by step here. First of all, what is the total signal voltage at the output?
GM on
In terms of voltage, then it would be V square by R, right? Like power.
1 second, 1 second. Your voltage, signal voltage. What is the gain from input to output? What is the gain from input to output here? This is the input,
GM1 into
output. GM1 into,
RL.
right. So this is GM1 into RL, right?
Yes.
This is the small signal gain. So what will be the signal voltage at the output?
Input.
GM1 R V naught or VI.
Right?
Yes.
And now, okay, so this is your signal output, right? Now what is the power?
Squared divide by RL, right?
GM1 times RL times VI, the whole square, right? We have to find out total output voltage, right? The total output voltage is this thing, and you have to simply square it, right? Why are you saying divide by RL?
So that's how we used to find the power in a circuit, right? Like it should be V square by R or I square R. Power loss or power
Oh, okay,
dissipation.
okay, 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 I get
It
you.
is different.
Okay. No, so yeah, so here when we say power, I mean it is basically voltage square. Okay, not anything else.
Acha.
Okay,
So you're assuming the RL to be 1. Like,
I mean something like that. I mean you're not assuming anything here, but that's how it is calculated, and you're doing it. Okay,
okay, sir, go on.
yeah, cool. So yeah, so and power will then again some bandwidth p. Anyway, so this is how you calculate your SNR. Now moving on to the second question. So basically the point of this question was not those technicalities, but yeah, so the main point of this question is that this M2 cannot contribute to noise unless there is some path here, right? Something here. So now that is where the third question is. So assume a finite CP. Now the CP here is not 0. Now it is some finite CP. Find out the SNR at V0. So what will happen to this CP?
Some path will be provided.
Correct. So basically, and how do we find out? So that is the question. So let's see. Again, we have to do the same exercise again. So this is the third question, third part. Assume finite CP. Now the now what will happen? And let's take the first one. Take IN1 first. So in that case, what will be the picture? What will the picture look like? It will be this is CP, right? And this is your noise current source at the output, IN1. This is grounded, right? This is also grounded, correct? And you have this RL here, and this is output. Okay. Now tell me, yeah. So this is M1, this is M2. Now tell me what will be the contribution. Due to this IN1, what will be the voltage out, V out? Yeah, go on. Anyone?
I1 times RL parallel that capacitance, impedance of the
How come?
capacitance.
How come? How did you
So
get
there are
that?
two parallel paths. Like one is through RL and the other is through CP.
How did you get that, man? That's not true. Yeah, think. What will happen now? Whenever you have this problem, right? Finding out how to track what is parallel what. So you just track how the current, what will be the behavior of the current. So if there is if there is a current flowing here, okay, and if it sees two parallel paths, so what will happen to this current?
It's a current division.
There will be current division, right? So tell me, this current here, IN1. Let's assume that this IN1 is flowing in this direction. Okay, direction doesn't matter here for IN1 because this is a noise current, and ultimately we are going to simply take its average, squared average. So direction doesn't matter here. So I can as well take this direction here. Okay. So let's take this direction here. It is going to flow in this direction. Now tell me, when this starts flowing here, and when it comes here, what will it see? By the way, what will happen to this M1? What is the condition of this M1?
Sir,
M1 is
off.
M1 is off. So let's turn it off. Okay. Now tell me what will happen to this IN1 current, this current here, as it comes.
it will see two resistances. So I mean two impedance. So
Correct.
one is over 1 by GM2
Correct.
and another is 1 by SCP.
Correct. Exactly. So there will be a current division here, right?
Yes, sir.
And what current will flow here into RL? What will be the current flowing into RL?
1 by SCP
No, one
divided
second.
by
Don't
1 by.
don't tell me the expression. Tell me which current. I mean, in this and this current, which current will be flowing through this RL?
I in one plus the current through the CP.
Are you sure? I mean, there are the current here. Sorry, this current IN1, it started flowing here. It saw two paths. One is in this direction, one is in this direction. So it is split, right? Now tell me which current, which out of these two split currents, which one will flow into RL? Will it be this current or will it be this current?
Oh, okay, so
Sir,
there is
upper
some
one.
upper.
Upper one.
Correct, upper one, right? So this will be the current, right? So what will be the current? So what will be that current?
Like so, 1/8
It will be basically
CP.
IN1 times the GM2, right, divided by GM2 plus SCP, correct?
Yes.
And because of this is IN1, right? Now and what will be the voltage due to this? So this is the current times RL, right?
Yes.
Am I correct?
Yes.
Cool. So this is the the output voltage, right? SV out due to IN1, correct? Right?
Yes.
Good. So this is SV out of IN1. Cool. Now this is done. Now let's move on to the to IN2. Now take IN2. So what will be the picture looking like? This is IN. This is the second MOSFET, the first MOSFET. This is the grounded. This is grounded. There is CP here. There is this noise current here. IN2. This is grounded. Then this is RL, and we have this V out. Okay. Now tell me what will be the contribution of IN2 to RL, and what part of it will flow into RL? First of all, will some part of IN2 flow into RL or not? Yeah, it will. So what will that current be? How much will that be?
Sir, IN2 itself.
Sure. Are you sure? Why are you saying that? So you are saying that all of IN2 current will flow through RL. So why do you say that? Again,
Sir,
so
RO2 is infinity, so and the lower transistor is off, and only CP is present. So I think there is only one current flowing through the circuit.
1 second. So again, direction doesn't matter, right? For IN2 current, direction doesn't matter. So I will take this direction here. Okay? Right? I'll take this direction. Now, now tell me when this current starts to flow here, it will have what will it do?
So it will split.
Again, and where will it split?
So one component will going through the capacitor CP and another through MOSFET.
Correct. Right? And what will happen to this MOSFET here?
Second MOS is sir off.
Correct. So
Second
this is
MOS.
off. So this is out of picture. Okay? So this is off. And only there are two currents. One is through this, one is through this, right? And what is this is M2, by the way, this is M1, this is GM2, this is anyway off, so it doesn't matter. So now tell me what will be the and out of these two currents, one is flowing through CP, one is flowing through this MOSFET M2. Out of these two currents, which current will flow through RL?
CP current.
Huh?
CP current.
CP current you are saying. Why do you say CP current?
Sir, if we assume it as a black box in that
Correct. Exactly. So that is what I wanted to hear. Good, very good. So if this is a black box inside, this is inside a black box. Okay. So any current which will enter through this has to leave through this black box, right? So there is only one current which is leaving through this black box. So this is the current that is going through CP. So only that current can flow through RL, right?
Yes.
Correct. So tell me, what will be the current through RL?
So A is CCP divided by
IN2
ACP
multiplied
plus.
by basically SCP divided by SCP plus GM2.
GM2
Correct? Oh, sorry. Yeah, GM2, right. And what will be the voltage?
into
Multiplied by
RL.
RL, right? So it will be minus RL, right? Here, by the way, it will be minus RL because current direction is in this way. So it will be minus RL. But anyway, so we will square it, so it doesn't matter. But yeah, so for consistency, we have to put it. So this is SV out due to IN2. Correct?
Yes, sir.
Cool. So now what is the what next? So what is the total? Okay, so by the way, there is a small minor mistake here. When you write sorry, when you write power spectral density, okay, you never write in terms of S. First of all, this is not SV out. This is only V out due to IN1. S is basically power spectral density. This is not power spectral density. This is only output voltage. Okay. This is also only output voltage. Okay. Now, to find out the power spectral density, what do? Replace S by J 2 pi F and take the magnitude square. Okay, so everyone understood that whatever I just wrote?
Yes.
Yeah. So SV out IN1 is what? It is IN1 times GM2, IN1 times GM2, or in this case SIN1 times GM2 divided by into RL the whole square divided by GM2 plus 2 pi F CP whole square. This is square and again the whole square. Is that clear?
Yes.
Yeah, cool. And what is SV out of IN2? This is right. So it is actually equal to SIN2 times 2 pi F times CP times RL whole square divided by 2 pi F CP square plus GM2 square and then the whole square. Correct?
Yes.
Right. Now, so that is why, what is the total spectral density? It's equal to SV out IN1 plus SV out of IN2, which is equal to SIN1 times GM2 plus SIN2 times 2 pi F CP whole square divided by multiplied by RL square divided by 2 pi F CP whole square plus GM2 whole square, isn't it?
So, sir, why this square term is coming here? Because we are taking the magnitude and the square. So,
Correct. Yes. Oh, sorry. My bad. Yeah. Thank you. Thank you. There will not be any square term. Cool. Thank you. Right. So is this clear now?
yes.
Yeah. So this is the total power spectral density. So if you have to find the total power, what will you do?
Integrate.
Correct. Integrate of SV out times df 0 to infinity. So here since we have assumed there is some parasitic capacitance here, okay, there is some parasitic capacitance here, Cp will actually limit the bandwidth of the circuit, okay. So we do not need to explicitly put a bandwidth B here, we can integrate it from 0 to infinity, okay. In the earlier circuit, since there was nothing that was limiting the bandwidth, you see that in this case the noise power here is actually independent of frequency, isn't it, the noise spectral density. And if we integrate it from 0 to infinity, we will get simply infinity, right? So that is why we assume that there is some finite bandwidth B of the whole circuit. So but in the second case, you can see that the SV out is actually a function of frequency, and it will decrease as frequency will increase. So that is why now we can integrate it from 0 to infinity, okay.
Yes.
Fine. So when you integrate it, you will get the answer. So I encourage you to do this calculation. You will basically revise your class 12th integral calculus. There is some basically replacing the variables by another variable. So here you will be needing that tan theta sec square theta replacement. When you do that, you will get the answer. Cool. Let's move on. So the main point of this question was what? To have this to basically understand that this M2 is basically it will never contribute to any noise if the total if basically there is no path for it to flow. Basically, if the output resistance of M1 is infinity and also there is no parasitic capacitance Cp, then this M2 will not contribute to any noise. It is only when the when this M1 has some output resistance or this parasitic capacitance, only then does M2's noise come into picture. Okay. In general, the noise contribution of M1 will be the maximum. Okay, this is a cascode circuit, isn't it? This is a classic cascode. Understand it, right? This is a cascode. You know what is a cascode? You know what is a cascode?
Yes.
Yeah, so this is a classic cascode. So for any cascode, in general, the noise contribution of this cascoded transistor M2 is basically very less compared to the noise contribution of M1. Okay, the M1 is the highest contributor of noise for a cascode device, for a cascoded circuit. Okay, so this is the takeaway from this particular exercise. And
Noise is always uncorrelated.
yeah, it is noise is always uncorrelated, right? I mean, noise of two different devices are uncorrelated.
If it is correlated, what are the changes in the expression?
Which noise are you talking about? What? How can the noise be correlated? I mean, that is what I am asking. Noise can be correlated only when it comes from the same device. If there are two different devices, okay, any two different device, the noise will be uncorrelated. If the noise is correlated, then you cannot do this exercise here. So what we did here, right?
We cannot add directly the power spectral
You cannot
densities, right?
add the power spectral densities. Yes, we'll have to take this cross correlation term also here.
Some
Okay,
extra factors will come.
This is the extra factor which will come.
Okay.
This is basically the cross correlation, in1 times in2, the whole mean of that. This is called cross correlation. So this will not be 0 in that case. We'll have to take that into account. Okay. Okay. So this question is done, right? And there is a similar question like this in your assignments also. So I don't think you will have any difficulty in attempting that. Okay. So moving on to the second problem. Let's do the third problem first. Yes, this is the better one. So you can you know that, right? This is a current mirror, right? This is a current mirror, right?
Yes.
Correct. So it's a simple current mirror. Now we are simply multiplying this current. What will be the current ratio between this MOSFET and this MOSFET here? N, correct, right? And since the current flowing through this MOSFET is I naught by N, the current flowing through this is I naught, right?
Yes.
Correct. Now, so this is a 1:2 N current source or current mirroring. So in this particular question, so to reduce the power consumption overhead, so you know that you can also make a 1:1 current mirror, right? 1:1 current mirror. So for 1:1 current mirror, what will you do? You'll have to make this current source here I naught. Mute yourself everyone, please. Yeah. So I was saying that to make the current source, to make it a 1:1 current mirror, you will have to increase this current source here I naught by n to I naught, right? And after that, when this is I naught, and if this is that, then in that case the size ratio will be 1:1 here. Instead of n, it will be 1, and then you will have this 1:1 current mirroring, right? But if you increase the current here, the power consumption will increase, right? It will increase, right? And the purpose of this particular transistor is to simply provide a reference voltage, right? This MOSFET here, this second MOSFET, this is the one which is whose current matters, okay? And this is the MOSFET whose current matters to us. So this MOSFET here is simply there to provide this voltage here at its gate, okay? So that is why there is no it doesn't make much sense to simply increase the current in this particular MOSFET, right? It will simply increase the total power. I mean, we can also use this I naught by n and 1:1 current mirroring to ensure current I naught flowing through it, right? And in that case the power consumption goes down by n times, isn't it? So that is why the question is to reduce the power consumption overhead, basically total power consumption, I decide to have a current I naught by n in the reference branch, okay? Instead of I naught, we use I naught by n in the current branch. Now, how do the power consumption and noise compare with 1:1 current mirror? So let's do this, right? So take two, basically we have two cases. We have a 1:1 current mirror which has this particular situation, which is like this. This is I naught, this is MOSFET here, another MOSFET here, and the current in this is I naught, right? And this is 1:1, correct? This is 1:1 current mirror, and we have another 1:n current mirror, which is exactly the same thing. So you are not getting disturbed by the noise here, right? I mean, in my locality some noise is there, so you're not getting disturbed by that, right? Okay, cool. So if anyone gets disturbed, please tell me. Anyway, so this is in this case we have I naught by n current flowing here, and this is instead of n 1, this is n, this is 1, okay. By the way, this is diode connected here. Okay, so this is the situation. Now tell me, what will be the power in this power consumption? Let's say the power consumption is this is this, the power consumption is P. Okay, let's say the power consumption is this is P.
Sir,
So, yeah.
sir, power consumption means the power consumed by both two transistors, right?
Whatever things are there inside it, they will everything will consume some power. So total power consumed. There are two transistors here. Then there is this current source also, right? Hello.
Yes, sir.
Yeah. So, is that clear?
Yes, yes.
Yeah. So power consumption, let's call it P. And what will the P contribute? P will be what will be the constituents of P? So the constituents of P will be this part here, okay, everything inside this and this part here, correct? So let's call this power as some PF, and let's call this as some PV, okay. or let's call it PD, and let's call it as PM for P mirror, and this is PD for P diode. Okay,
Okay, sir.
fine. So it will be P equal to what? Power consumption will be PD plus PM, isn't it, in this case? Okay,
Yes, sir.
and what will the power consumption here? Come on.
So PG by N plus PM.
Correct. It will PD by N plus PM. So natural. So obviously in this case, in this second case, the power consumption is less, right?
Yes.
Yes,
Correct.
sir.
Now let's talk about the noise contribution. Now let's talk about the noise contribution. So tell me, what is the noise in these two, in both of these? Yeah, tell me what is the noise. Yeah, go on. First of all, identify the noise sources. Whenever you are told to find out a total noise, first of all you have to identify what are the noise sources, from where all we can have noise. Okay, that is the first target. That's the first thing to do. So in this case, what all things can contribute to noise? So what do you think? What all things can contribute to noise in this case?
Two MOSFETs.
These MOSFET and this MOSFET, right? Only these two have the noise contribution. I mean, again, I assume that this current source is ideal and it does not contribute any noise. Okay, so we have only two noise sources, this guy and this guy here. Okay, now let's find out what is the total noise. So
Can you write the expression for PD and PM?
come again.
Can you write the expression for PD and PM?
Okay, so what is PD? You only tell me. How do you calculate power? What is PD?
Voltage into current.
Yeah, so what is the voltage and what is the current in this particular part of the circuit? Yeah, tell me. Hello, are you there? Okay, so anyway, this is the voltage. Sorry, the PD part is actually VDD times I naught. Okay, yeah, and PM is basically I naught times whatever. So basically, this part of this part, I can only comment on it simply in terms of this. Okay, so maybe I can write it. So this is I naught, current is flowing through this MOSFET. Okay, and this will be again coming from some supply. Okay, this is again be coming from some supply. So let's call that VDD prime. So this is basically PM is VDD prime times I naught. Okay, and in this case, since it is so you can simply see that current I naught is scaled down by n times. So the same VDD, but current is reduced by n times. So that is why PD is reduced by n times. But in this case, PM again, this is the this part here. This is nothing is changing, right? Current I naught is flowing here also, and they will both come from the same supply VDD prime. Okay, so that is why PM is same. Cool. So let's move on. Now let's think about the noise contribution. So we have the following situation here: VDD, this is I naught, and we have this MOS here, and the noise contribution of this MOSFET is something of this kind. This is diode connected here. There is another MOSFET here. Noise of this is like this, and then there is this. So whatever current flows out, let's call it I out, not I naught. This is I naught. Okay, this is 1:1. This is this is M1. This is 1:1 current mirroring. Fine. So what will be the noise due to M1 at the output? So which is our output of interest, by the way? What is our output in this case?
Output current
Correct.
and
It is the
IO.
output current that is of interest to us, right? So we have to calculate what is the noise contribution of IN1 and IN2 in the output current. Okay. Earlier we were calculating output voltage, right? But now we are calculating only output current. Is that clear?
Yes.
And to find out the output current contribution, an easy way to do is that simply short the output. Okay, simply short the output. Okay, and then find out how much current is flowing here. Okay, is that clear? I am only
Yes.
interested in the output current, right? I am not interested in the output voltage. So if I am only interested in the output current, I can simply short it, right? And since it is shorted, the output voltage will be anyway zero. So, but we are not bothered about the output voltage. We are only considering output current. Our only interest is output current. So we can simply short it here. Okay. Fine. So
Yes.
now tell me what will be the current this I out. What will be I out because of IN2 and IN1 individually? Or total I out? Tell me.
So IOT will be IN1 plus IN2.
I out will be what?
IN1 plus IN2.
No, no. Think carefully. Okay, so take everything step by step. So what will be the again here also we can use superposition, right?
Yes.
Yeah. So what will be the so take IN2 first. Okay. So how much IN2 will flow
Yes.
out? What will be I out because of IN2? What
So
will be?
that is IN2 only.
Correct, because any current that is going simply flows into the ground. There is nowhere else. Means ground is the shortest path, right? Least resistive path. So it will simply prefer to flow through that. Okay. Cool.
Yes.
Correct. Now what is I out due to? Sorry, what is I out due to IN1?
So is it GM2 by GM1 into IN1?
Exactly. It is GM2 by GM1 to IN1. And how did you calculate that?
Because INO1 see a resistance of 1 by GMO1.
Correct. Right. So
That is
correct. So it is basically IN1 then first flows through here, right? And it sees that it has a resistance of what 1 over GM1, right? So the voltage that will develop here will be IN1 divided by GM1, correct?
yes.
And this current, because of this voltage, an output current will flow here, and that will be equal to how much? IN1 into IN1 divided by GM1 into GM2, right?
GM.
So it will be
Yes.
IN1 into GM2 divided by GM1, correct?
Yes.
This will be IN1 divided by GM1 into GM2, correct?
Yes.
Right.
Here GM1 is equal to GM2. So
No, we have not. How is GM1? Ah, yeah, right. Yeah, GM1 is equal to GM2 here also. That is why it is equal to IN1 plus IN2. Oh, so that is why
yes.
you were saying that it is equal to IN1 by IN2.
Yes.
Okay. Fine. So, correct. So, total I out is simply equal to IN2 plus IN1 into GM2 by GM1. But since it is a 1:1 current mirroring, since 1:1 current mirror, so what do we have? GM1 equal to GM2, right? And what is the expression for GM1 equal to GM2? What is the expression? It is
To 2 mu and dx.
right,
Yes.
correct? This is GM1 and GM2. So that is why we have total I out in1 plus in2, correct? So
Yes, sir.
total sin out, it is equal to sin1 plus sin2, correct?
Yes, sir.
And again, since both are again equal, so in1 equal to in2, right? I mean sin1 equal to sin2, isn't it? That will be equal to 8 times kt gamma gm 1 or 2, whatever you want to say, correct?
Yes, sir.
Fine. So this is the condition here. Now take the second one. Now let's take the second case for this. Let's put a partition here. Okay. Now noise contribution. Fine. Again, so what will be the noise contribution? How will you calculate? So this is VDD. Okay. This is I naught. We have, sorry. Again, we can ground it, right? And this is like this, and this is the noise here. This is in1, this is in2. This is 1, this is n. First of all, this is m1, this is m2, and this is 1 is to n, isn't it? And this is I naught by n, correct? Right?
Yes, sir.
Okay. So now tell me what will be I out due to in2?
IN2.
Correct. Again the same thing due to in1.
That will be n times I.
No, but the expression is same, right? in1 divided by gm1 into gm2, correct?
Yes, sir.
Right? Now what is the relation between gm2 and gm1 in this case? What is gm2 and gm1 relation?
GM2 is equal to n times GM1.
Is it? Is it n times? Or is it root n times?
So GM is equal to
GM2 by GM1 is n.
Are you sure?
Yes. GM2 by GM1 ratio is n.
How come? That is what I am trying to understand.
Because GM is equal to mu n C of W by L into VGS minus VTH.
Yeah, right. So I was just trying to confuse. So basically, if you look at this one here also, so some people might get confused that W by L is simply n, and that is why it is root n. But you see that I naught is also scaled, right? So it is actually equal to n. Yeah. So you actually use the correct formula. So it is VGS minus VTH. That is easier to comprehend. Correct. So this is n times GM1, right? Fine.
Yes.
So now tell me what will be what will be I out due to in1 in that case? in1 into n divided by in1 into n, right? Correct.
Yes.
So now what is the total I out is equal to in1 into 1 plus n, right?
Yes, sir.
Correct. So what is total sin out? Sorry. What is it?
Plus n
in1
whole square.
square into 1 plus n the whole square. Sin1 square to 1 plus n का whole square, right? So it will be 4 kt gamma gm1 1 plus n the whole square, correct? Right now?
Yes, sir.
Correct. So tell me, and if you have to compare between this and this, so what is gm1 in terms of, so here you see gm1 is less than this gm, right? Because the current is different in this case. Hello?
Sir, can you repeat?
No, I am asking, is the gm here and gm here, are they different or not for m1? So between the two cases,
Yes, sir.
the m1 gm is different or not? That is what I am trying to understand. Hello?
Sir, no, sir. It should be same.
How come?
No. It's different. The second one, GM will be lesser
N times lesser,
in
right?
the first one. Yes, sir.
Right now. So it will be n times lesser. So gm, so this, let's call it gm, simply gm, okay, and let's call it gm1. So thus this gm1 gm will be equal to n times of gm1, right?
Sir, root n times.
How come root n times?
Sir, because the W by L is the same for both the
No,
cases,
wl is
and
not same for both the cases. This current I out is actually equal in both of this. This is I out, right? This is I out. This 1 and this n are actually same.
okay.
I mean, are you getting my point here?
Understood, sir. Because to reduce the power, we are just making I
Yeah,
naught by N.
correct. Yes, that is why. So, yeah, so now tell me, so is this correct, by the way, in that case?
Yes, sir. It should be.
Yeah. So, what will happen in that case? So, in this case, we have 4 kt gamma gm, or let's call it 2 into n times gm, right? And this is what? Right. And what is this? This is basically 4 kt gamma, and this is gm1 times 1 plus n the whole square, right?
Yes.
There looks to be some inconsistency somewhere. There is some inconsistency somewhere. There's 8 kt gm comma gm is equal to n times gm1. This is fine. So this looks to be some inconsistency somewhere. What is this? Have I made some mistake somewhere calculation wise? I2 is I1 by G1 to G2. This is fine. So what is G2 is actually equal to n times G1. This is also fine. N times n, n times n. Total I out is equal to oh shit. This is not correct. This is 1 plus n square only. This is not 1 plus n the whole square. This is only 1 plus n square.
Excuse me. In GM calculation expression, why we are using 2ID by VGS minus VTH? So VGS is fixed,
Okay.
that's why.
In this case, VGS is constant. Okay, easily. That is why.
Okay, okay. Suppose if you are using root over 2 I naught means that is will
That
getting
will
different.
no. This will also give the same answer. You have to just understand that I naught and WIL are both being changed here. Okay.
Here I naught is replaced by I naught by n.
Correct.
That's it. No?
And WIL is also replaced by the another quantity. Okay.
Okay.
Fine. So yeah. So here I made a mistake, calculation mistake. So I out 2 to IN1 is IN1 times n. Okay. And I out 2 to IN2 is IN2, simply IN2. So when I took both the total IN total I out, it is actually equal to IN2 plus IN1 times n. Okay. So when you take the SIN out, it will be SIN1, this will be SIN2 plus n square times SIN1. Okay. And what will it be? SIN2 is 4 kt gamma gm. Okay. Plus this will be n square times 4 kt gamma gm 1. Okay. And gm and gm1 are the following relation. This is the relation, n times gm1. So gm is n times gm1. Okay. So we have this is 4 kt gamma, and this is n times gm1 plus n square, or let's not replace this, let's do this here. 4 kt gamma gm plus n square times 4 kt gamma, and gm1 is actually equal to gm by n, right? Gm by n. So this is gone here. This is equal to 4 kt common, and gamma is also common, gm is also common, 1 plus n, simply. Okay. Is this clear?
Yes, sir.
Fine.
Yes.
Yeah, right. And here what do we have? Here we have 8 kt gamma gm, right? Here we have 4 kt gamma gm n plus 1. So compare this, both of this. So this gives you 4 kt gamma and times 2 times gm, right? And what does this give? 4 kt gamma gm times 1 plus n. Correct. So you can see that for n equal to 1, both of these are actually equal, right? Which should also make sense, because n equal to 1 is simply 1:1 current mirroring. So this and this are identical, right? In that case,
Yes, sir.
the
Yes.
both of these noise currents also should be same only, right? But for n equal to greater than 1, what happens? This term becomes larger, right?
Yes, sir.
For n greater than 1, this term becomes larger. So the moral of the whole story is that if you do 1:n current mirroring, you will definitely save in terms of power. So power consumption in this case, in the second case, is definitely less than the first one, right?
Yes,
But
sir.
when you do 1:n current mirroring, you will definitely save in terms of power. But what will you lose? What will you lose? You will actually see that,
Noise is more.
yeah, noise is more in the second case. Okay. So this is the moral of the story, that when you are trying to reduce the power consumption by increasing the order of this current mirroring, be careful that you are also increasing the total noise. Okay. So this is the moral of the whole story. Now let's see whether we can do some other question also. Let's yeah, so this too you should try on yourself, on your end. So I guess today I will be leaving you early. Okay. So these two questions you should try on yourself, by yourself. Okay.
Hello, sir.
Yeah.
Sir, I have a doubt in question number one,
Yeah.
part C.
Yep.
There we have divided the current I into and not considered the resistor RL in current division.
Uh,
Part C.
part C. Okay. Finite CP, right? So let's come down here. Yeah. Now tell me.
Yes, sir. There we have used the current division of I into,
Iron two, right?
and there we have not considered RL. Like CP and RL should be in series, na?
Why do you say that?
Like because same current will flow through CP and RL. Like if I join RL and CP,
Hmm. Okay. Okay, that's okay. Let's think about it. Okay. Hmm. So the current here comes here, comes down, goes go through that RNCP, and yes, it looks like it is in series. Yeah, it's actually in series. What is it? Yeah, it's actually in series. Yeah, I was wrong here. It's actually in series. Hello?
yes sir.
Yeah, it is actually in series. Yes, it is in series. Yes.
Okay, sir.
Yeah, it is in series. Yes, you are right. It should be. Yeah. So it should be changed here. So it will be what I into CP and RN series. So what will be the equation for that? It will be SCP plus 1 over, sorry, it's RL plus 1 over SCP, so it will become 1 plus SRL CP and divided by SCP, right? If you take its inverse, it will be SCP divided by 1 plus SRL CP. This is the one. Fine, so it will be, yeah.
Yes, sir, but if we take the small signal, like suppose we did disconnect a MO1 CCP and also the noise source IN2 also, and if we connect a taste voltage signal, that is Vx. So in that case, the current going inside the source of the MOSFET M2, that is the GM2 into VPX, right?
Correct.
So from so that means test is equal to GM2 into V test. So from that expression we can derive that Vx by Ix is equal to 1 by GM2. Right. So if the resistor is in series or not, it doesn't matter.
No. He's not talking that. He's saying that this path here, second path. Okay. This is actually in this the current flowing is through CP and RL, right? This is the current path, right?
Okay.
This is what he's saying.
Okay.
Is it clear now?
Yes. Yes.
But yeah, 1 second. I mean, that's not
But
actually
sir,
true.
equation was right, right?
No. One
Equation
second.
was right.
The that guy who asked me, you see that the current is definitely flowing in this manner, but we have assumed that this is ground. Okay, we have assumed that this is ground. Hello.
Okay. Okay, sir. Yeah.
Yeah. So when we assume that this is ground, so the current that will be flowing here, what will that be? I mean, we have explicitly put a ground here, right? There is a ground here. Let's say you have RL here, RL, and then there is a CP here. Okay, and we have put a ground here. So what will be the current flowing through here? I mean, if there is a current flowing here, if there's a current IN flowing through here in this, so what will be the voltage here? It will be IN divided by SCP, right?
Yes, sir.
It will not be IN divided by SCP plus anything else, right? It will be IN divided by SCP. It means that basically what I'm trying to say is that definitely IN, this RN and CP are in series, but still when you because since we have assumed that this is a reference voltage, this is a ground here, that is why the current, this voltage that will be generated here will actually be equal to the thing that I said earlier, that this will be SCP divided by 1 plus divided by GM2 plus SCP. Okay,
Okay, sir.
is that clear?
Yes, sir.
Yeah. So other way to look at it is in this manner. So what you can do is that let's assume that let's forget everything. So you know that again we have to find this V out, right? So one way to do this, one other way to do is that you assume that RL is not there, okay, and you short it. You short output and assume that, and you find out the short circuit current. Whatever current is flowing in this, you assume that RL is not there. First remove RL, short it, ground it, okay, and find out how much current is going into the ground, okay.
Yes, sir.
And then after you have found out the total current that is flowing into the ground, you simply multiply that current with the with this output resistance, whatever output resistance you have. So in this case there is only RL, right, since this part is infinity anyway. So you see that is the total voltage. So that is in that, if you do that, you will get the same answer here, okay.
Okay, sir.
Yeah, fine. So let's leave it at this. So I just want to discuss the two questions only. So other two questions that I have not discussed today, I would like you to attempt them. If you have any doubt, you can ask me in the next session, okay. The first question that we did should help you in solving your assignment for this week, okay.
Okay.
Yeah, so let's call it a day today, okay. Let's again meet this next week, okay. Thank you for joining today.
Thank you,
Thank you
sir.
everyone. Yeah, welcome.
Thank you, sir.